Once again, I want to welcome you to my YouTube channel. This is the Bright Stars Academy and my name is Mr. Arnold. This is our second lesson on calculus and we are still on differentiation 1. But before I forget, please don't forget to subscribe, like and share. In our lesson 2, we are also going to discuss differentiation from first principles. But before we begin, I would like us to know the aims of this particular lesson. In this lesson, we are going to learn how to differentiate fraction expressions of functions. We are going to elaborate more on how to differentiate them from first principles, how to also differentiate third expressions from first principles. Later on, we are going to learn how to deal with both the fractional and the third expressions, and also understand the logic that is involved in this. Afterwards, we are also going to go through more revision on this area so that we have more comprehension of this particular area. Alright, let us go through our lessons beginning with the fractional function. These expressions are in form of fractions such as x plus 2 over x minus 3, x squared over x minus 2, x cubed over x minus 3x squared, and so on and so forth. So they can come in so many ways, but what we need to know that these expressions can be linear, quadratic, or polynomial depending on the degree of the variable term. And they are also solved using our 4-step rule that was later discussed in our first video. So if you are not able to go through our first video, I would encourage you to go through it so that you know how the 4-step rule that is going to help us in differentiating from first principles. However, in this case, we are going to apply some little algebra and we are going to generate a new rule which is also going to help us in the process of solving such numbers such that we don't find any challenges in this concept. But you need to know that all these expressions are going to be in form of y is equal to u over v, where u and v are functions of x. Like for example, if I take a close look of this one and this expression, it's like our u in this case is going to be x plus 2 and our v is going to be x minus 3. Now, what happens when we differentiate? On differentiating, the derivative is going to become dy dx, whereby it's going to be us getting this this function which is at the bottom, multiplying it with the derivative of this other function u minus the function u multiplied by the derivative of this one at the bottom over v, the function which is at the bottom, squared. Now I want us to see how does this expression that I've just written down here come about. So let us take a close look and see. Right about now, I would like us to know how to derive this formula that we have just discussed about from first principles. Now, considering that this is our formula, y is equal to u over v, our very first step is that we are going to introduce small increments, and therefore it's going to become y plus small change in y being equal to u plus small change in u over v plus small change in v. Afterwards, we are going to make small change in y the subject, and it's going to become u plus small change in u over v plus small change in v minus u over v, because this u over v is the y that we have taken across signs and it is being represented like this. Then after we are going to make it one composite fraction by combining it. So using the knowledge of O-level algebra, we shall have v into u plus small change in u minus u into v plus small change in v over v into v plus small change in v. Afterwards, we are going to simplify it further, but we need to note that we do not tamper with the denominator, and this becomes the new logical rule that we are going to apply here. What do we mean when we say do not tamper with the denominator? We are trying to mean that when you look at the way how the denominator is being represented, is the way we are going to keep it up to the end of our expression. Then after then we shall apply our last rule, whereby we shall then simplify it further to get our functions. So I would encourage you not to tamper with the denominator. What I'm trying to mean, like simplifying it, expanding it, and so on, it might lead you to making a lot of errors in your algebra. Then after then, we're going to simplify further the upper expression such that we have v small change in u minus u small change in v over v into v plus small change in v. You can see again I've not tampered with it. When you go further step, that is dividing by small change in x, therefore it becomes small change in y over small change in x. Again, you do not tamper with the denominator, you only tamper with the numerator. As you observe here, it's going to be u small change in u minus u small change in v over x, and down we shall have v into v plus small change in v. When we continue further down, we are going to realize small change in y over small change in x is going to be whereby this small change in x can now only divide small change in u and also divide small change in v. Now we go to our last step. This last step is when we take limits. When I take limits as small change in y over small change in x approximates to dy dx, where the small change in x approximates to 0, that implies that this expression, which is having small change in u over small change in x, is also going to approximate to du dx, which is the derivative of the function of u in respect to x. And also at the same time, small change in v over small change in x is going to approximate to dv dx, and small change in v is going to approximate to 0. Therefore, our expression is going to be in this form, but since we want it to look like the previous one, we need to note that du dx is the same as the derivative of u, keeping in mind it's in respect to x, and also dv dx is also a derivative of v in respect to x. So when we substitute in these expressions here, we shall have dy dx being equal to this derivative of u minus u derivative of v over v squared, and that is our expression. At this juncture, I would like us to go through these examples in fraction expressions such that we get to know how best we can apply this concept. Now, taking our first question, that find the derivative of the function y is equal to 1 over x squared from first principles. Now, if we take a close look from our previous steps, we are going to have our expression. We are going to do our very first step whereby we introduce small increments, and it becomes y plus small change in y being equal to 1 over x plus small change in x squared. Then after that, we are going to make small change in y the subject, whereby it is going to be small change in y being equal to 1 over x plus small change in x squared minus 1 over x squared. The next step was to make it composite. So when we make it composite, this is how it's going to be. It's going to be y, small change in y being equal to x squared minus small change in x plus small change plus x squared over x squared into x plus small change in x squared. But remember what we said, that when we get our overall denominator, we do not tamper with it up to the end. So we shall continue to simplify further, whereby this when we expand this one using perfect squares, it's going to become this. But remember that this negative outside is going to affect all of it. That's the reason why all this is negative, and therefore this x squared is going to go with this x squared. Therefore, from that step, we are going to divide by small change in x, and on dividing by small change in x, we are going to have our expression becoming y over small change in x being equal to negative 2x minus small change in x, because the small change in x goes with one of them here. It also goes with one of these ones which are squared here. But remember, in all those steps, we do not tamper with the denominator, whether expanding it or simplifying it further. From there, when we are taking limits is when we now remember about our expression. So dy dx as it small change in x over small change in y over small change in x approximates to dy dx. That means that small change in x is going to approximate to 0. So wherever we see small change in x, we are going to put there 0. So when we simplify further, our dy dx is therefore going to be negative 2x over x squared times x squared. Why? It is because here where there was small change in x approximated to 0, therefore we had negative 2x minus 0 on the numerator. Then on the denominator side, this one approximates to 0 such that we remain with x squared into brackets xc again squared, because this is 0. That's the reason why we are having this. And this implies that our expression is now going to become negative 2 over xc cubed. Why? Because one of the x's here is going to go with the one on the numerator, such that we remain with this expression, implying that d into brackets 1 over x squared in respect to x is going to be approximating to that, and that marks our final answer. Then here I give you the second example for more clarity. So again, you're going to realize that again these are the same steps, but always you just need to be careful with your algebra. So in our first step, we are going to introduce small change in small increments. It becomes y plus small change in y, it being equal to x plus small change in x plus 1 over x plus small change in x minus 2. Afterwards, we are going to make small change in y the subject, as you see, whereby from there we're going to make it composite. Now here you have to be more careful with your algebra, that this one at the bottom is going to multiply this minus this other one at the bottom is going to multiply with this x plus 1, and then over this one multiplying with that one. Now here you have to be more careful with your algebra, such that when you are expanding, this is going to become x squared, as you see here, plus x small change in x, as you see there, plus xc alone. Then this negative 2 is also going to multiply this expression, whereby we're going to have negative 2x minus 2 small change in x minus 2. Then also when expanding this one, we're going to have negative x squared, as you see here. Then this negative x is going to multiply here, which is positive, which gives us negative x small change in x. And again, this negative x is going to multiply this negative 2 to give us positive 2 x. Yeah, there was an x here. Then afterwards, this negative 1, because this negative multiplies this and becomes negative times this to give us negative x, negative we're going to also have negative x multiplying with this small change in x to give us negative x small change in x, and this becoming positive 2 over our denominator, which we said that we shall never tamper. When we continue further, we are going to divide by small change in x, and when we divide by small change in x, we are going to realize that we are going to simplify further, first of all here, by removing those ones that are similar, and then we shall have this expression whereby we shall divide it by small change in x, which will become negative x over 2 over the same denominator as the previous one. Then afterwards, when we are introducing small increments, as small change in y over small change in x approximates to dy dx, that means small change in x is going to approximate to 0. That means wherever we have small change in x, like this one here, is going to approximate to 0, such that you remain with x minus 2 times x minus 2. Then when we will look at it further, small change in y is going to therefore become negative x minus 2 over x minus 2 times x minus 2, and again here it's going to therefore become negative x minus 2 over x minus 2 squared, and that's how our expression becomes that. Alright, hoping that you have understood fraction expressions. If you have not understood, I would like you to continue repeating to understand the steps clearly, such that as you go to this other next session of our video, that you understand the third expressions. Now let us look at third expressions. These expressions are represented with a root symbol with a power raised to 2. I want you to note that you can hear about those ones raised to 3. Those are not third expressions. They are in form of, we can see here, root of into brackets ax plus b. We can also have, like for example, we have root of 2x, root of 2 plus x. We can also put a cartoon there to just confuse you. Still, it's the same thing, root of x squared plus 1, and so on and so forth. The roots that are raised to power n, whereby n is higher than 2, are solved differently. So I want you to note that when we are solving them, we shall solve them differently, and that means that we are going to use what we call Taylor's expansion first, and then eliminate some of those small appearings which requires you to apply knowledge of numerical methods. But remember, for us, we are sticking on our 4-step rule. So when we are differentiating surds can be expressed in 2 ways. We can apply what we call the rationalizing logic, or indice binomial expansion of implicit functions. But for me at this juncture, I would encourage you using the rationalizing logic than you using the indice binomial expansion logic of implicit functions, because it might become a bit hectic and a bit confuses you in your expansion, because again at the end of the day it will require you to use at some point Taylor's method, which is rarely taught in A level. But if you want more videos about this, please you can comment about that, then I'll be able to share with you how to use the indices binomial expansion of implicit function. But I would encourage you that the best way is this one, and it also has less steps for you to have already got the answer that is required. For that one, you have been able to talk about the Taylor's method that you will apply for binomial expansion. But I would like you to keep in mind, if we are to use our logic here, that our 4-step rule still works through the logic applied that you would use. Alright, now let us know how to differentiate third expressions step by step. Let us consider a third expression in form of y is equal to square root of ax plus b. Of course, our very first step is to introduce small increments, and it becomes y plus small change in y is equal to square root of a into x plus small change in x as then b. Then we say that we have to make small change in y the subject, whereby to become square root of a into x plus small change in x plus b minus square root of ax plus b. At this juncture, you realize that we cannot move further ahead, and therefore we need to apply the other rule that we have just discussed about, that is the rationalizing. So we shall get the conjugate of this 2 and then of these two sides that are subtracting. So it means to get the conjugate, it means that we are going to multiply the same two sides, but whereby the sign here changes to a plus. But since we are rationalizing the numerator, that means that we have to multiply the conjugate on the numerator and also on the denominator, which was out of 1. After doing so, we realize that this upper part, the numerator, is in form of differences of 2 squares. So on further simplifying these differences of 2 squares, we are going to have this. Now, when you further simplify, you're going to realize that the square roots are going to die out, and the purpose was to remove the square roots such that we can be able to subtract what is inside to simplify the number. So when we do that, remember when you create a denominator, I remember telling you that in our previous slides, that when you realize that it's a fraction and you are having a denominator, kindly do not tamper with that denominator, leave it the way it is. Let us focus mainly on the numerator, but keep on writing the denominator the way it is. So when you further simplify this expression, you're going to realize that this 2x, this a is going to multiply and becomes ax plus small change in plus a small change in x, then plus b, and then minus ax minus b. Now this negative ax is going to go with this positive one, and this positive b is going to go with this negative b, such that we only remain with the a small change in x over this expression. Now when we further simplify by dividing by small change in y over small change in x, realize that, remember what I told you, you only tamper with the numerator. So this small change in x is going to go with the other small change in x, such that we remain with the a alone. When we take limits, that's where now we shall tamper the denominator by just eliminating anything with small change in x. Small change in y over small change x approximates to dy dx, as small change in x approximates to 0. Now that's when we shall come and approximate this to 0, such that we remain with a into x plus then into a close brackets then plus b, which looks similar like that. So that means that our dy dx is therefore going to be this expression. Now when you further simplify, it's going to be dy dx being equal to 2 to a over 2 into ax plus b, because these ones being similar and having the same base inside, that means that we can be capable of adding them using the laws of surds. But let us note some few information here, that you need to apply rationalizing whenever you have a surd. Wherever you realize that there is a surd and you are going to differentiate from first principles and you're using rationalization method logic, always know that rationalizing is important, although we shall need to know when. Then also the rule 5 of non-tampering with the denominator still happens here, as we realize it here. We kept this one here, we kept it until when we're carrying out limits. That's when we tampered it by eliminating a small change in x, so it's still here applies. And let us take note on your algebra skills as you work out these expressions. I want you to always be careful, because it can involve a lot of negatives and positives, as we are going to see in the exercises that we shall do, and also in more examples that we are going to do in this video. Let us go through these examples to know more how to apply this concept. Here is our very first question, where they're telling us find the derivative of the function y being equal to root of x from first principles. Remember our very first steps: introduce small change in x and small change in y. Small change in y plus small change in x is equal to root of x plus small change in x. Make small change in y the subject, it becomes x plus small change in x minus root of x, as you see. Then small change in y, when we simplify further by rationalizing, we are going to realize that we are going to multiply the conjugate both on the numerator and the denominator. Then we further now start simplifying the numerator without disturbing the denominator, and this, remember, it's going to be differences of two squares, such that we can now multiply them in this form. And on further simplifying them, we realize that here it's not perfect squares, it's only the square root that will go such that you remain with the inside, which is x plus small change in x, and even here you remain with negative x. This negative x is going to go with that x such that we remain with the small change in x. Now by dividing small change in y over small change in x, we are going to have here small change in x over small change in x without tampering with the denominator, and remain with 1. Then afterwards we are going to take limits whereby we're going to have y small change in y over small change in x approximating to dy dx as small change in x approximates to 0. Now that leads us to come and tamper with the denominator. Where we find small change in x, we eliminate, and that means that you're going to remain with the square root of x and then plus square root of another x. And this is what is going to happen. Small change in y over small change in x being equal to 1 over square root of x plus square root of another x. Since both of them have the same base inside, we can now add them and emerge them as 1 as dy dx being equal to 1 over 2 root of x. And therefore, that is our final answer. Now let us look at our second example. In this case, they are telling us that find the gradient of the function of the curve y is equal to square root of x minus 2 from first principles. Applying again similar steps, we're going to introduce small increments, small change in y plus small change in x being equal to the square root of x plus small change in x minus 2. Making small change in y the subject, it becomes square root of x plus small change in x minus 2 minus square root of x minus 2. When we rationalize, because from here there is no any other step if you do not rationalize. When we rationalize the numerator by multiplying the conjugate on the numerator and the denominator, we are going to end up having differences of two squares, whereby the square roots are going to multiply the square roots there. And when further simplifying these square roots, when it goes away, we are going to remain with the x minus 2 plus small change in x. I've just interchanged by taking this one this side and this one here. And then when you remove also the square root, you're going to have this negative x here. Then plus, because this negative is going to multiply with this negative to make it a positive. Those are the steps I'm always talking about in integers that I want you to pay more attention at when you are working out these numbers. When you further simplify this number, you're going to have small change in y over small change in x being equal to small change in x over small change in x over the denominator that we do not tamper. When you further continue, you're going to have that. And small change in, when we take limits, small change in y over small change in x is going to approximate to dy dx as small change in x approximates to 0. When you further simplify, remember when we take limits, this one here is going to go to 0 such that you remain with x minus 2 there, such that these two are similar. When they are similar, that means that we can emerge them as 1. And therefore our expression, our dy dx is going to be 1 over 2 square root of x minus 2. With all the knowledge that we have been able to collect, I would like you to go through these simple revision questions such that you improve on your skills. I've got for you one of the questions from CJ Tranta. I would like you to give it a try and you see how you level based on how you're improving in these numbers. I've also given you another question which comes from Pure Math, L. Boston and Sadler. Then our next question has come from again CJ Tranta, A-level, Advanced A-level Mathematics. And now I have another question which I have obtained from which I've set on my own. I would like you to go through these questions. Thank you for watching this video. I would like to take this opportunity to thank you for watching my video. But before we continue, I would like you to give a like, share and comment. In our third video, we are going to go through the following. We are going to differentiate trigonometrical functions from first principles. We are going to differentiate explicit functions from first principles. I want to also show you that we can also still differentiate explicit functions, although some teachers do not emphasize teaching it. And I'm also going to teach you how to combined expressions, and also we're going to do more revision that area. But whenever you find difficulties in any of those numbers, you can please comment and request for help in any of those numbers, such that we can develop this knowledge together. Please like, subscribe, comment, and share with many to be able to help you. May God bless you.